Okay, welcome to lecture number 46 and let us continue to apply Laplace transform technique to solve electrical network problems. In my earlier class, I solved a simple RL circuit, how to do it. Now, I will be a little bit more formal with each of the elements and their Laplace transform. For example, I will say that I have a resistance R, pure resistance, and it is excited with a voltage, any voltage it could be, but only thing is this voltage is applied at t equal to 0. Before that V t was 0, that was that will be always true. This voltage I have applied, I am interested to find out the current. Of course, in a resistive circuit one need not go to Laplace domain to solve it, but to make the idea clear, let us proceed like this. So, in this case I t is equal to V t by R straight away, V t into U t by R, that is known. But what I will be doing is here this equation itself is what is called an algebraic equation, no differential term, but nonetheless let us take Laplace transform of both the sides. So, Laplace transform of both the sides if you take, it will become I s, Laplace transform, which I want to know, and 1 by R is there, R, and Laplace transform of V t u t is V s. Therefore, you see the Laplace transform of the current is equal to Laplace transform of the voltage divided by R. That way we should start interpreting the thing. Okay? And resistance is a memoryless device, therefore, its initial current does not matter. So, present value of the current is decided by the present value of the impedance, that is all. So, nature of V s and I s will be same. So, I s is equal to V s by R. That is, I will say Laplace transform of voltage, because voltage by some impedance is current, we know. So, Laplace transform of voltage, input voltage divided by the impedance. Impedance in general, here it is only R, no inductance is there. Let us take inductance separately. For example, here L, here you have applied a voltage V t and there will be some current I t. What is V t? V t into U t I have applied. Therefore, here of course, the voltage current relationship will be I V t U t applied voltage is equal to voltage drop here, that is L d I dt, L d I dt, and this will be equal to L d I dt, is not. I want to find out I t is what. So, I t does not appear here explicitly in the form of differential. I take Laplace transform of both the sides, Laplace transform, you take of both the sides. So, left hand side will be V s and right hand side will be L into S I s minus I 0 minus. This will be the thing. If I 0 minus, mind you this point is important, if I 0 minus is 0, then I will say V s will be simply equal to S L into I s, or I will say the current. What is the excitation here? The input voltage. Current will be simply V s, Laplace transform of the input voltage divided by S L. So, with initial condition relaxed, the current in an inductor can also be expressed in the same way as we have done for resistance, some voltage divided by some impedance. Voltage means Laplace transform of the voltage divided by impedance, which was R. Similarly, here I should say L T of voltage, Laplace transform of voltage divided by impedance. Now, this impedance, in this case if you write it, it is like impedance in S domain, mind you, impedance. When I will tell about this impedance in S domain, that is how it is. So, if it is an inductance is present, the impedance offered will be S L, not L alone, like resistance only R. Therefore, with initial condition relaxed, this is true. Similarly, take capacitance. For example, a capacitance is there, C. This is the voltage, and suppose you have excited the capacitance with a current source I t, like this. So, I t is flowing like this. Now, voltage at any time across the capacitor is integral I dt by C, but as I told you earlier, I will be always try to write down the terminal voltage current relationship of a particular element in the form of some differential equation, and I know that what I know, C dV dt is nothing but I t, is not? This is the thing, C dV dt into is equal to I t. Take Laplace transform of both sides. So, it will be C S V s minus V 0 minus initial voltage across the plate of the capacitor is equal to your I s. Then I say if V 0 minus is 0, if the voltage across the plate of the capacitor prior to the this is I t into u t I have applied, mind you. So, I t into u t. So, if V 0 minus is equal to 0, then I will say C S V s is equal to I s. And I will say that okay, I s can be written in this form, that V s over 1 by C s. This manipulation you just note down. That is once again the current in the circuit is the Laplace transform of the voltage across that element divided by its impedance, which happens to be now 1 by C s. in S domain. Therefore, impedance of a in S domain, I summarize in S domain, resistive circuit, a resistive element R will appear as R only, no change for inductive element, that is L in time domain will appear to be SL. Capacitive element in time domain it is C, it will appear to be 1 over C s. This is the crux of the matter. These three things one has to remember. So, in time domain, if the circuit contains several R, L, C, in S domain you just replace them. If there is some S, you replace it by SL. If there are some capacitances, replace it by 1 by Cs, provided this inductor and capacitors have no initial conditions. That is, if it was an inductor, I 0 minus must have been 0, then only this linear relationship holds good. Therefore, voltage, Laplace transform of voltage and current, they form they maintain a linear relationship, because V s is equal to S L into I s, is not this is a constant S L. Similarly, for capacitance it will be V s is equal to 1 over C s into I s. So, this is the impedance of the capacitive element, and for resistive element of course, it remains as R into I s. Got the point, but this will behave as an S L and 1 over C s, provided the initial conditions are 0, that must be understood. Okay. I will tell you shortly how to take into account these initial conditions. So, one way you take the Laplace transform, write down the differential equation, write I 0 minus here, then take the Laplace inverse of both the terms, you will get the solution. That is fine, but I will tell you something else also, you can do it. What is the discussion I had in the previous page, how it can be now translated into. For example, I have a circuit like this. Now, what I am first let me tell, what I am trying to do is this. Okay, given a circuit, in time domain circuit will be given, for example, you are given a circuit like this, or a rather complicated circuit I am taking, R capacitance, and there is another resistance and another inductance is there, and suppose I am going to apply a voltage, and this voltage I will put now I will remove all the restrictions. This voltage could be anything including your impulse, no problem, because the Laplace transform of impulse is also known, which is 1. So, everything is so nice now. Now, suppose this is in time domain, this is the circuit given to me. This is suppose R 2, this is C 1, and this is suppose R 3, this is L 2, and this is R 1. This is the circuit given. I have been asked to find out the currents. Now, if I have been asked to calculate the current and I want to remain in time domain, see the involvement that would have been necessary. You have to assume this current I 1 in time domain, I 2, I 3, apply KCL here. Suppose I want to know only this current. What is this current? I want to know. Then I have to nonetheless write down the time domain differential equation. Will there be a differential equation? Yes, because there are energy storing elements apart from resistances. Then write down, form a differential equation. even using Laplace transform I am telling, what I have to do is this: if I want to find I1t, what is the thing? Form a differential equation in time domain This is step number 1. Step number 2 will be form a differential equation in time domain involving I1. Because I1t I want to know. So, I must form a differential equation out of these two loops, this, that, do something, get me one differential equation, and that can be done. Now, second step would have been that take Laplace transform of both the sides, take Laplace transform of both the sides. Then step 3, then get an expression for I1s, and finally take Laplace inverse of I1s to obtain I1t. These are the steps you have to follow, nothing doing. So, formally if you want to apply Laplace transform, first write down the differential equations, get this node voltage, do something to finally get a differential equation involving I1t alone, no I2, I3 should be there. Okay, then take Laplace transform, get I1s, etc. But this looks quite some sort of heavy load, I mean following these steps, even with Laplace transform I am telling. Now, can I do something better? Suppose I have been told that, suppose all initial conditions, I also tell this much, this information. Suppose all initial conditions of the energy storing elements are relaxed. What do I mean by this term relaxed? It means that these are 0, initial condition 0. Zeros, all are zeros. What does that mean? I1 0 minus will be 0 for this inductor. If you call this to be your I2 and this to be your I3, then I will say, so this means for this problem, it means that I1 0 minus is equal to 0, I3 0 minus, there is an inductor here, its initial current must be known, that is 0, and here is a capacitor, the voltage across the plate of the capacitor Vc1 0 minus is equal to 0. These things are given, suppose. If that is given, if this is known, then I will say for this circuit to find out I1t, you need not start from differential equation. What you will first do this is that draw this circuit, redraw the circuit rather, redraw the circuit in S domain. This you try to understand. So, circuit structure will remain same. So, it will be like this, there is a voltage source here, there is a resistance, there is an inductance here, and there is resistance here, capacitance there, and there is another resistance, another inductance is there, is not? Then what you do, all the time quantities here, replace it by its transform. So, B t, Laplace transform of B t is V s, write V s. All the element values, for example, resistance R 1 will remain R 1, all resistance will remain as it is, no change, R 3. Then the inductances, this was L 1, then you write S L 1, no J into S L 1, no, S into L 1, no imaginary number like that. In that imaginary thing sigma plus j omega within S it is there, but we do not care, S L 1. And this capacitance, so I will write 1 by C 1 S is its impedance in S domain. So, write all the impedances element wise in S domain, and here I will write S L 2. Once I do that, then I have gone to S domain, and is S domain what is the thing? V s is equal to I s into some Z s, and once you can write a equation involving voltage and current in this form, what I told you, you can revoke all the things we have learned in DC circuit in this circuit as well. In fact, we did this in case of while finding out the steady state currents of a sinusoidally excited currents or voltage in RL RC circuit, is not? V phasor equal to I phasor into Z. So, here also similar things happens, not only algebraic, but the relationship in terms of this equation Z s being constant, V equal to I R, whatever I did in resistive circuit, I can now do this here as well. Got the point? Therefore, this current will be I 1 s, this current I will say I 2 s, and this current I will say I 3 s. Now, everything in S domain. So, from this to this you just sketch it. What I am discussing about? I am telling you need not write differential equations. If initial conditions are relaxed, just redraw the circuit with the parameter values replaced in terms of phase as appropriate. If it is an inductor, it should be S into that inductor. If it is an capacitance, its impedance will be 1 over C 1 S. That is what we saw in the previous slide. Therefore, you do this, then you know V s equal to I s into Z s. Therefore, I will be able to apply series parallel rule of finding out equivalent impedance, things like that. Therefore, I will say now your I 1 s, look, follow me, very interesting. This is this will be equal to applied voltage V s divided by equivalent impedance between these 2 points. What is that equivalent impedance? These two will be in parallel. So, it will be R 2 plus 1 over C 1 s into R 3 plus S L 2, this z into this z by sum of these two z's divided by R 2 plus R 3 plus 1 over C 1 s plus S L 2. And this is in series with this. So, this will be equal to R 1 plus S L 1, S L 1, that is all. So, in one stroke I will get the expression of I 1 s. Then you, and everything is algebraic, no differential. So, manipulate this, do partial fractions and write down the right hand side, which will be function of s only, in such a fashion that you can easily identify if you take. So, finally, what you have to do? So, I 1 t will be, you have to take the Laplace inverse of I 1 s. That is this big thing, its Laplace inverse. With numbers, it looks quite a challenging task. Okay, in general I have written, if the numbers are there, I can always simplify this to some handy expressions and find out the inverse and get the value of the current, time domain expression of the current so easily. So, one way of handling this is go on writing down the differential equations, apply KCL, KVL, form a differential equation involving I 1 t alone, then take Laplace transform of both sides, get an expression of I 1 s. So, both these are Laplace transform method only, but what I am telling, after knowing that in circuits this R 1 L 1 will get translated into R 1 S L 1. So, it is an impedance Z 1. So, so people may write Z 1 S is equal to R 1 plus S L, just like that S L 1. Similarly, there is an impedance at Z 2 R 2 plus 1 over C 1 S, Z 3 R 3 plus J J R 3 plus S L 2. And since B s equal to I s Z s for each of the elements, therefore, I can invoke all the things I learned in DC circuit, V is equal to R I, and that was instrumental, from which I got the equivalent impedance expression as R 1 R 2 by R 1 plus R 2. All these things can be nicely applied here. But in this second method, in this method here, in this method, there is no differential equation I have written. So, I will translate this circuit in terms of S, and as if now it is a DC circuit sort of thing, like that I will manipulate the circuit, get the Laplace transform of a particular element and do it. Similarly, just last one point about this. Suppose I say that in this circuit also get this voltage V 3 t. Got the point? This voltage I want to know also in this circuit. How do I do it? You have known I 3 s, look these steps. So, I know I 3, just I am telling verbally, I 1 I know, Then I will calculate what is the voltage between these two points. It is V3S, is not? And what is the value of this voltage? The value of this voltage V3S will be I3S into Z3S. What is Z3S? It is R3 plus SL2, that will be this voltage. Therefore, if somebody tells me calculate this voltage as well V3TS, then I have to calculate V3S first, because I1S I know. If I know I1S, what will be I3S? I3S will be equal to the total current I1S into impedance of the other, that is R2 plus 1 over C1S, and then sum of these two impedances, sum. What is that? That is R2 plus R3 plus 1 over C1S plus SL2. This will be I3S, then I3S into Z3S will be this voltage, then take Laplace inverse of this one to get V3T. So, it is almost like analyzing a DC circuit. These are the greatest advantages of using Laplace transform. In my next class, I will tell you, okay, that is fine. I will give in a circuit, I will redraw the circuit in S domain, replace inductance by S into L, replace wherever capacitance is there 1 over C into S, then some sort of impedance thing I will get, and once I get impedance thing, everything is Vs, Is, etc. I will be able to find out the equivalent impedance, or I can even apply nodal method, this that, to get the currents. But all is fine, and you can avoid writing down the differential equation, that is another greatest advantage. But these things will be true provided there is no initial condition. In the next class, I will tell you how to still retain these advantages, that is avoiding writing differential equation, at the same time take the initial conditions into account. Thank you.